Hello, welcome to Chapter 10. In Chapter 10, we're only looking at two sections, 10.2 and 10.3. 10.2 is about correlation. I'm going to walk you through a couple key points here in the textbook before looking at some homework, and 10.3 as well. In Chapter 10, we are looking at paired data, sometimes called bivariate data, to find what is called the linear correlation coefficient. The letter we use for that is a lowercase r. We are only looking at linear relationships at this time. There are other types of correlation, but we are only looking at linear. A correlation exists between two variables when the variables of one are somehow associated with the other. In other words, as one increases, the other increases, or as one increases, the other decreases. And so if we plot those pairs of points, those values, and we see some sort of a pattern that's approximately close to a straight line, then we can call it a linear correlation. You saw some scatter plots in Chapter 2, and here are the examples, some more scatter plots. You can see that some of them, as you scroll down this page, have specific patterns and others do not. This one has a positive correlation, this one has a negative correlation. This one kind of looks really scattered, and there really is no correlation whatsoever. In letter D, we are looking at one that has a relationship, but it is non-linear, so we would not be looking at that type of question in this section. So we're going to be computing correlation. If you were doing it by hand, you would be looking at a formula that looks like this. You use your x values and your y values because they come as ordered pairs, and you do a lot of squaring, adding, multiplying, and dividing. However, our software is going to do that for us, so please do not do this by hand. A couple things that we do need to know, however, is that the correlation values are always between -1 and +1 inclusive. Even if you convert the values of variables to a different scale, the value of r will not change. So for example, if you have people's weights in pounds and you convert to kilograms, the correlation is not going to change. R measures the strength of the linear relationship between those, and it's very sensitive. So adding one extreme value can make a significant difference. Let's look here at an example. It says finding R, and give us a particular value, the shoe print of a person and the height of the person, and we're looking to see what the correlation is, and it's 0.591. That's a smaller sample. Walking through the formula here, 0.591, looking to see if there is a linear correlation. You then take your results and you're going to compare it to table A5 in your textbook. And in that particular table, it indicates that we had to have a value beyond 0.878 or negative 0.878 in order to be significant. So we would say there's no correlation, there's no significant connection between those two variables. Now, when we square r, we get what's called something about variation. And if we square the value of r, what we find is the percentage of variability in our dependent variable that can be attributed back to the initial independent variable. So for example, if we look at shoe prints and heights, we could say, well, if we took the correlation of 0.813 and we squared it, we get 0.661, and that would indicate that 66% of the variability in heights could be linked with variability in shoe print lengths, which means there are other variables involved. And obviously, we all know that it's not just height and shoe size that are connected, but there are other factors and variation in height that cannot be explained by how large your feet are. Moving on to section 10.3. In 10.3, we are looking at what's called regression. And this is where we are going to be going back and visiting that concept from algebra called y equals mx plus b, or slope-intercept form. In 10.3, we're looking to find an equation that best fits the scatter plot of the data. And so here's your regression equation, y hat equals b naught plus b1x. And of course, the coefficient of x is your slope, or the steepness of your graph, and b naught would be the intercept if you were plotting it. X is your independent variable, or what we call a predictor variable, and y is your dependent or response variable. Again, we're not doing this by hand. StatCrunch is going to do this nicely for us, but you can see the formulas are here. And we're going to, of course, use technology. You can see some different examples here of other technologies as well. And then what can we do with these particular equations? So for example, if we have an equation here, what can we do? Well, if you take a look at this one here, where the cursor is pointing, you could, for example, put in someone's shoe size and predict their height. These equations are great for finding the predicted value for one of the variables. Of course, you can also plot them and graph them to compare them to your original data. Now, strategies for predicting y. Can we use the equation all the time as a model for y? And the answer is no. If you have a significant correlation and the scatter plot kind of indicates that, you've got a line there and you go ahead and compute, then yes, it's a good model. However, if you do not have a significant correlation, then no, the regression equation is not a good model. And the only thing you can do then is use the average of y as the best predictor. So please keep that in mind. You will see homework problems where there's no significant correlation. It asks you to predict. The only thing you can use then is the average of y. Now, let's take a look at a couple homework problems here just to kind of talk through. You might open your homework for chapter 10 and say, I think she might have made a mistake. I didn't. This particular one asks you to find the y-intercept and to graph the equation. The slope here is 1/6. That means for every 6 that x increases, y will increase 1. And there's no y-intercept. It's like we said, y equals 1/6 x plus 0. So you would go ahead and use your line tool to indicate the intercept is at the origin, and then you would go 1, 2, 3, 4, 5, 6, up 1, and then plot your line. Now you might say, well, what does this have anything to do with chapter 10? And again, in chapter 10, we're looking at regression, and I am going to be asking you questions related to these graphs and understanding the graphs and intercepts. So we're doing a quick review here in the beginning of some basic algebra skills. Same thing with numbers 2, and then we go on to 3, and it says a high correlation indicates the relationship between the two quantitative variables must be linear. So you want to think about that. As we talked about, not every correlation in the chapter is linear. Correlation coefficient can be 0, whether that's true or false. Again, a little concept question. April calculated a coefficient between the gender and GPA as negative 0.25, and that's a fairly weak one. So you want to take a look then and to see, does that make sense? Is that a meaningful statement? For number 6, we're looking at results from another software where the value of the linear correlation coefficient is 0.967. Remember, the largest it can be is 1, so it's an extremely strong correlation. And we want to determine if there's a linear correlation between the chest size and the weight of the bears. So we want to look at, first of all, the table of critical values to see if that's meaningful. Now we have 8 bears, so we would look at this table, and we would look under 0.05 because the problems of the significance level is 0.05, so 0.707. So if our correlation is greater than 0.707 or less than negative 0.707, we would say yes, there's a significant correlation. So the answer here is yes, because our value, our test statistic, is greater than 0.707. So that's the first part. Then it says what proportion of variation in weight can be explained by the linear relationship between weight and chest size. And this is what we call, remember, we looked at this before, R squared, or the variation. So we're going to go ahead and square R. And in this particular case, you can get, maybe something a little over 0.90. And then that would be the value that we would enter in here, 0.967 times 0.967. And then round to 3 decimal places. So take your calculators, and we're going to enter 0.967 squared, round to 3 decimal places. In this particular case, 0.935, again, a little over 90%, 93%. And then that's it. We're done with that question. Kind of the same process for the next question. Now, in number 8, we're looking at data on a graph. And so students sometimes say, well, where's my data? Well, you're going to have to take the points off of this graph and enter them into StackCrunch. So, for example, one of our data points is 2, 10. Another one is 8, 1, 8, 2, 8, 3, 9, 1, 9, 2, 9, 3, 10, 1, 10, 2, 10, 3. Those are your points, and you will enter them as pairs in StackCrunch and have StackCrunch compute the correlation for you. Same with number 9. Now, number 10, you do have data to compare. And so they start off by, of course, what would be our null hypothesis, that there's no significant difference that there's no significant correlation, and take it from there. Let's open this in StackCrunch and just quickly take a look at how to do correlation. So again, here's our data. And we would click Stat, and we click Regression, and we would click Simple Linear Regression. And our court income and justice salary are what we're looking at. The hypothesis test is that there is or is not a difference. Let's see, is there a linear correlation? So we're looking for, if there's a correlation. So this is set up correctly. So we're going to go ahead and click compute. Here is our equation, regression equation we could use to predict. Here's our correlation. And if you click the right-hand arrow, you will of course see the graph, the scatter plot with the fitted line showing in red. So it's easy for you to see that. And now you can look back at the problem and take your work from there. Similar type of problem. Here are the regression equations. Again, what's the key difference between these two? Keep in mind that one of them is for a sample and the one is for a population. That's why we have different notations. Remember, anytime you see something with a little hat, that indicates the sample data. Here's a predictor equation, and we have some values, and they want us to determine the best predicted value by plugging in. Another one with your little points. A couple more with those. Here's another one where you're going to find the correlation between systolic, diastolic, and find the regression equation right from StatCrunch. Here's one for listing and selling prices of houses. And finally, closer to the end here again, I'd like you to watch a little video and just get some quick concept questions, again, about regression and correlation. Hope that helps. That should get you through Chapter 10, and then it's on to Chapter 11, the very last one for our semester. Good luck!